Hello, everyone, and welcome to the first, a little bit more official lesson. We did, of course, have the lesson yesterday where you looked through that video, and we looked at the weird way that what we're seeing can affect what we hear. And then this video, I hope you found it pretty interesting. The kind of the explanation of that. A lot of the stuff you see in this video are things that we're going to be able to learn a lot more about in detail, and just kind of have like a better understanding about things around us, the physics of the world around us, right? So the fact that different sounds are made up of key simple frequencies. Every single one of those simple frequencies, usually it's a little bit more like they're saying here, like a trumpet. These are all just individual perfect sine waves. Like a sine wave is like this, right? Like my mouse is going through a sine wave pattern. So a whole bunch of sine wave patterns, specific ones. If you had just this one, just this one, just this one, just this one, and so on all the way along, it would sound like a trumpet. A true trumpet sound has even more, of course, but it's in that pattern. So the fact that complex sounds are made up of a bunch of, and surprisingly few, simple sounds, surprising, and it's something we'll get to see. I didn't know actually this. I had never heard of this. The idea of if you have all these harmonics, your brain will fill in this low one. So you hopefully heard the two sounds he gave at the beginning of the video. That there was one that sounded like it had a lower sound in it, even though it was made up of a bunch of sounds, some higher ones. That perception that you hear, a lower one that doesn't even exist, is kind of weird. It's just your brain trying to make sense of the world around it, right? That's what all illusions are based on, essentially. What was the other part I wanted to mention? The 12:10 was the timestamp of it. So which 12:10? Oh yeah, when he was talking about the words, like what word am I saying? What word am I saying here? Bear. Am I saying bear or bear? The exact same audio. And if you're seeing his lips closing and starting, then you're interpreting it as bear versus bear. And that really helps explain that the videos where what you hear depends on what word you're looking at. It's just, again, your brain getting primed to interpret a certain way. Very, very just odd, interesting stuff. This part I have to listen to again with proper headphones, because I didn't get the full experience because I was, at the time, I didn't have headphones set up. But hopefully you had it where in your left ear or right ear a certain voice was emphasized, and then afterwards you could hear what they were saying, because you're primed to listen for that sound or that voice. It's just weird, neat stuff. This one too, that the beat frequency, which we'll learn all about beat frequency, but the fact that the beat frequency still happens, even though it's not actually destructively interfering, a concept we're going to learn specifically about, and see and hear and whatnot. The fact that it's destructively interfering in your brain, in your perception, rather than physically actually destructively interfering in the air, I find really odd, and I'll make note of that and emphasize that when we get to that lesson. So that's the first time I've used this video as an intro, obviously, because it just got dropped, just got made and whatnot. But I super like it because the stuff that we start out with here isn't necessarily as like, it might be hard to see what the cool things are that we're going to lead towards. Let's put it that way. So it was a perfect video to lead into it. I'm going to use it forever from now, for sure. Beginning. For in-person classes, so I can ignore that part. For help times, just before we get going into the physics rest of it here, just some more first of the year stuff that I want to make sure I don't forget to mention. Extra help times, anytime really, because you can click on the help icon, which I think I can find for you quick enough here. In our D2L site or whatever, click on the post questions, and then boom, it brings right to it. You just say start a new thread. And I think maybe I already showed you guys what that'll look like, but I will just click here in case I'm thinking of something else. My course from last semester, it worked really well. So in here, you can see all these questions for help. There was 15 threads. I started doing it later in the year. But basically, people would ask a question and then everybody gets to see the help. And sometimes it was a student posted it in, Brent posted something, Ty posted something. Other times I just posted stuff that someone emailed me, whatever. It all works. It's best if you just post it right in there, but if you're shy, no big deal. I can help you out. Okay. So that's the getting help stuff. People that are in the building with me, of course, I'm available as well. So period 2 and period 4, room 124, lunch 124. Basically, you're going to find me down at 124. Okay, and just come by and see me. So click or come as often as you need. Just quick here, a story back when I was in grade 10, I guess, going into grade 11, and I remember specifically my dad asked me, what courses do you have this semester, Greg? And at the supper table, right? And I said, well, I have math, and I have chemistry and English or whatever. And then I said, physics. And I remember my dad saying, physics, what's that one? And honestly, I didn't know what to tell him. I had not much of an idea of what to tell him. I couldn't really pick out any of the key physics words. So maybe press pause and think of as many key physics words as you can if you're into it. I have a link here to the Big Bang Theory where Penny is trying to figure out what physics is so she can relate better to Leonard if you're a Big Bang Theory fan. And he's like, what is physics? And he talks about, starts at the history of physics, like Galileo or whatever. It's just silly. I won't play it here. You can play it yourself. So hopefully you end up thinking lots of things like, magnetism, gravity, and sound and electricity and I don't know, light or whatever else I haven't said. There's all sorts of nuclear particle physics. There's all sorts of branches of physics, of course, right? I like to say that if I'm trying to promote the discipline, I like to point out that a lot of the really cool things that people find interesting are physics. Like, why is the sky blue? Right? Think about what your answer for why is the sky blue. Maybe I'll get you to add it in on your post here. Just a brief, nothing major, just brief bit about why you think this. Why is the sky blue? Do you think? And don't Google it. Just think about what's your answer when you're submitting this stuff. Just put on, and why is the sky blue? Okay, so let me just add that in here. Why is the sky blue? What's your thought on that? I'll add that on there for you. And we can take it up later on. Remind me if I forget. I'm a little forgetful once in a while. Okay, but it's like cool dinner or topics of conversation are quite often physics related. Anyways, you're here preaching to the choir. I guess maybe you're here and already signed up for it. So let's get going. We have Unit 1 kicking in here on waves and sound. And so this is what I would normally start with, which isn't as exciting and interesting as that video, of course, right? But we know what we're working towards. So there's two fundamental types of waves. There are mechanical waves, and there are non-mechanical waves. They call them ethereal waves. And I'm going to just go to this actually. Call them ethereal waves or aethereal waves, depending on how you want to pronounce it. So mechanical waves require a physical material to travel through. Sometimes that material is referred to as a medium. So a water waves, the medium is the water, and so on. Sound is a mechanical wave. The medium, of course, is air. And I'll show a demonstration later on that sort of proves that. And other examples include water waves, earthquakes, and so on. I already mentioned water waves, but that's the main focus of this course. The aethereal or ethereal waves do not require a physical material to travel through. Okay, so they involve fluctuations in the electric and magnetic fields. What we're talking about is really electromagnetic radiation, which is light, radio waves, and microwaves, and radar, and cosmic radiation, and X-rays, and electromagnetic waves. Okay, those are it's a wave, but it does not require a material. So that's pretty broad overall general information that eventually you'll learn a lot more about. Hopefully you learned about electromagnetic waves a bit in grade 10 in the light unit. Probably didn't seem like that big of a deal, right? But it's way bigger of a deal than it seems. And to really start to remember that microwaves and red light and visible light and so on are actually part of the same thing, even though it's not obvious, is important. Side note, actually, how that was discovered. Interesting. James Clerk Maxwell was working on equations to describe and explain everything to do with electricity and magnetism. Separately from that, there were people that were trying to learn about light. And at the time in science, they had no idea they were connected, right? And so the light scientists, they measured the speed of light directly, essentially, and found it was 300 million meters per second, a very specific number. Separately from that, somewhere else in the planet, James Clerk Maxwell got that number out of his equations. He calculated based on the theories and the equations for electromagnetism that the speed would be 300 million meters per second. And so basically put A and B or two and two together and get four. And they realized like, oh my goodness, light and electromagnetic waves are actually one and the same. They're the same stuff, just different energy levels or versions of it. So weird, wild stuff. So mechanical waves, continuing here. The first thing we're going to talk about is vibrations, right? Because they are the source of the mechanical waves. Okay? So a vibration is just a repeated pattern of movement. It relates to something you might have heard about in a math class about periodic motion. So you end up with like this sine wave that I already kind of mentioned, talked about. So if you're not haven't done grade 11 math yet, just know that you're going to learn math equations to do with this. And it's called sinusoidal curves, and this specific one is a sine wave. There's also cosine and tangent waves. Not something that's critical for the course, but just to help put the information all together eventually. So we're going to talk about pendulums, masses on a spring, and ruler twang. And so I've got the demonstration link ready for us here.
Hey everyone.
That's me.
Here. Just a couple quick demonstrations for the first bit here. Not the most exciting one in the world, but we'll refer back to them in a little bit actually too for something. So this first one here, in the lesson video, you'll see described as a periodic motion. It's a pendulum. Periodic motion because it has a very specific pattern of movement that it repeats over and over again. Also considered oscillatory motion because it has a defined equilibrium, but periodic motion is all we're really worried about.
So it has a defined equilibrium spot. If you think of like a clock, the hands on a clock going around and around, that's also periodic motion, but it doesn't have an equilibrium. But again, that's more specific that we don't need. So moving on.
And when we refer back to it later on, I'm going to show you, so I can come back to that video. I'm just going to do it and we'll talk about it later.
Watch what happens here.
So look at what you see what you're noticing.
So I don't have any control over which the rate that goes back and forth at. It's up to the length. You're hopefully noticing that it's going kind of faster and faster there, and then we have words to describe that shortly.
Okay. Next type. Other periodic.
You have to remember not to clank things down on the table so hard next time.
Motion of mass on a spring. So that's obvious. Mass on a spring, periodic movement. Motion there.
Slam.
Versus this heavier one for comparison and discussion later on. And so I'll do it one more time.
So it's again a repeated pattern of movement. You can tell that one's faster.
Light one versus heavy one. Small mass versus large mass, whatever. And the last one in the lesson we're talking about tonight is the.
Just trying to decide where to show it here.
That's a repeated pattern of movement. There's even actually some sound to do with it, which links into the course as well. Good old ruler song.
Okay. Might not be your favorite song, but it's got a lot of the same notes. That's what a radio station said a long time ago. So those are the types of vibrations I'm just showing there. And so we've got pendulums, we've got mass on a spring, we've got the ruler twang going on, right? So in the pendulum, the repeated pattern movement is like it goes all the way over and then all the way back. Or it could have started in the middle and gone this way and then back or whatever, right? So that's either way you look at a full repeated pattern of movement. The one where it goes from the very left and back would be like this, I suppose, on the sine curve, right? If you look in this area here, let's draw your attention to it in the video. So yeah, that would be like the red one, like that. And then I guess the green one would have been more like the starting version here. I don't know if I want to do green or not, but you get it, right? The green one would have been this from here to here, like that. Anyways, and so yeah, it's movement to the left or the right. If you're showing it graphically, you might show it like the farthest to the left and the furthest to the right. It's just switching vertical. That's why I have the L and R on there for you. The mass on a spring bounced up and down. It goes all the way down, all the way up. And so your pattern could be from the top all the way to the bottom and back up, or it could have been from the middle down to the bottom and back up, or whatever. I guess most naturally, you might think of it as from the bottom, right? Pull it down, let go, and it goes up and then back down, right? Lots of different versions of the complete pattern that we could talk about. We're going to talk about amplitude shortly, so technically I wasn't supposed to reveal that yet, but it's not the end of the world. We'll come back to it. And then the ruler, obviously, same kind of thing. Okay, those are just vibrations. And the idea that we're hearing sound to do with it links, obviously, to the next things we're going to do in the course coming up. So the definitions we're going to get under control for this lesson are cycle period, amplitude, frequency, and phase. In phase or out of phase. So let's do that. So the cycle is those patterns that I was showing. So the red one, if you start at the bottom, and so on and so on. So it's one complete pattern of that movement. And there's a picture to go along with it. So it could have been, like that or that kind of thing, as long as it's a pattern that repeats over and over again. So if I were to clone, I'm going to use my mouse for this. If I were to clone that, you can tell it's going to keep going. And if I were to clone this one, clone's just what it's called in the program I'm using, right? So either way, you end up with the same thing, right? So just giving you the idea of it. So I better separate that slightly so you can get the idea that we got that pattern, right? So yeah, that's a complete pattern of the vibration. Period is the time, the amount of time, number of seconds that it takes for one cycle of the vibration to complete. Okay, so we've got the units in time and seconds. That's part of the idea of the international units. I'm just going to add in here time for one cycle of the vibration. To complete, it's all tied back to that source, of course, right? It's where the wave, or eventually we're going to be talking about waves anyways, came from that vibration. The System International Units, SI units, they call them. It's System International. It's actually French origin. Is seconds for time, and it's meters for distance and kilograms for mass. So you get your meters, kilograms, and seconds, and then those units combine to describe most other units there are, like speed, for example, is meters per second. Lots of different ones, right? Or we'll look at acceleration and force and all the different types of units. Even like newtons for force is really just based on kilograms, meters, and seconds, which we'll learn all about. The symbol for period is a big capital T, because P was already used for momentum, which starts with an M. So figure that one out. But M was already used for mass, and it was just a snowball effect, right? A for amplitude, thank goodness. It's just your maximum displacement or movement from the rest position. The rest position being that equilibrium where it would naturally sit if it wasn't vibrating. Okay, so it's your max displacement from the rest position. And so in the pendulum case, you just measure sideways out, like I had shown, or up or down in this case as well. So I could add in amplitude here for this one. So distance sideways from where it would rest, distance up or down from where it would rest are your amplitudes. Okay. And then frequency. So frequency, we're going to look at equations for that tomorrow in the next lesson anyways. So it's the number of cycles that occur in a given unit of time or per unit of time. And so the frequency at which you fill up your car with gas or go to the corner store for something or whatever. And so we think of it as like 3 times per week or whatever, right? It's just always going to be in seconds here. So number divided by time. If you go 3 times per week, that'd be a frequency of 3 per week, right? Here, if we had 3 times per second, it'd be a 3 per second, or 3, the fancy name for it is hertz, named after the James Hertz, I think it is. Anyways, yeah, so James Hertz, James Joule. I don't know, I'm not good with names. Anyways, so frequency, the symbol in the equation is F, and the units are hertz, Hz, or 1/seconds, right? Literally, this is what it is, and this is just the namesake used. That's why it's a capital H for hertz. Henry Hertz? Man, I better look this up. It's Henrik or Henry or something like that. Hertz. The rental car Hertz physicist. Heinrich. There you go. Heinrich. That was close. Well, in the end, when I said Henry or Henrik or whatever, Heinrich Hertz. There we go. Correction made. Yeah, and so then the last part is the idea of in phase or out of phase. I didn't do a video of this one. I can later on. In fact, there's sort of a weird one coming up. But if something are in phase, they're swinging together, right, in unison. If they're out of phase, they're the exact opposite. Out of, they're not in unison. When one's all the way left, one's all the way to the right, or when one's all the way up, one's all the way down. Okay, so you're in phase or out of phase, or somewhere in between. Okay, so that's just about vibrations themselves. Now, just because everybody likes silly videos to do with things, I found some videos where we have vibrations in weird situations. So go to videos here for you. So funniest, I'll just type in and it'll come up. Planet's funniest animals and dogs. So this one is maybe gonna play.
It's the planet's funniest animals.
So basically, the quiz would be, what does this have to do with this class?
I'm not sure what the windshield wipers are saying, but they're obviously fighting words. However, I can tell what the dog is saying, but I'm not allowed to repeat that on television.
Anyways, so the windshield wipers, of course, it's a vibration. It's a repeated pattern movement. It's periodic motion. It's a vibration, and so on. So it relates. So I can show it. Metronome. So metronome. This would be metronome weirdness here. I'm just going to show the first bit because the rest of it is to do with metronome. Did I not spell that right? Metronome. Let's go with that one. So, good old-fashioned metronome. Whoa, that's a lot of vibrations, right? Now, I am going to come back to that one later, and you're like, I'm just sort of piquing your curiosity as to why someone would do this. And what else do I have here? Funny cats. Everybody likes funny cat videos. All right, funny cats. Funny cats. Funny cats. Wire? Yeah, of course. Must be the one. I don't know if it's right or not. Yeah, it is. So again, this one's a stretch, of course, right? But is it a repeated pattern of movement? Yeah. Is it adorable? Yeah. Anyways, it's just ridiculous, but it's for fun. And the school bus wipers, obviously it's just wipers again, right? But we're going to come back to, let's go wipers. We're going to come back to this one for reasons we'll talk about, or you'll see soon. But the school bus wipers, each of those are a repeated pattern of movement, obviously. All right. Okay. So we're gonna hear. So we'll see and hear this again later. What happens when things are in slightly different frequencies and they're alternating in and out of phase. So I'll just play this one here. Pendulum multiple, actually. Let's do that. You don't have to wait for ads. And there's a multiple, and it was Wave. Very cool. Yeah, it was the first one that's coming up. Almost. So what you're going to have here, it did show you briefly the different lengths have different rates that they are, different frequencies that they vibrate at. And so you can see all these different lengths, right? And then see what happens as they are kind of going in and out of phase. So at some point here, you could probably picture like, okay, this pink one here and this yellow one here are out of phase and so on, right? Watch for maybe those pink one and the yellow one to get in phase eventually. Oh boy, computer's slowing down here. Oh boy. There, pink and yellow are kind of in phase right now, right? And so on. So the weird patterns you're seeing are just a bunch of phase changes, alternating from being in phase and out of phase. But it does surprising things. It's two different, like you sent two different vibrations, and so on and so on. So I will let you watch the rest of that one if you like on your own. Weird stuff, do with phase and so on. You're just looking at questions 1, 2, 4, and 5 for this one. And why is the sky blue? It's not a right or this isn't about whether you get it right or wrong. I'm just curious what your thought is on why the sky is blue. Please don't look it up. Just what's your gut feeling about if someone said why is the sky blue and you could win $1 million if you answered, whatever. Just what do you think the answer is? Okay, it's not for $1 million, unfortunately. All right. So hope that works for you. If you have any questions, email me, or if you have any help questions, post them in the post area there. And hopefully I haven't forgotten anything. All right. Like to press record or something. Just kidding. All right. Talk to you later. Bye.